Started recording again. Wait a little while. Okay, well, hopefully we're recording, and so let's get started, sort of to review what we did. So we started off with SpinEcho. So our plan is, we start off with SpinEcho, and then we said, well, that's really slow. It takes 40 minutes, and then then we have fast SpinEcho, FSE, which is faster. And then today we'll start off with 3D fast SpinEcho, which is faster, and you can make smaller voxels, but it's still not quite fast enough. And then we get to really fast SpinEcho, and that's what we use today. So if I just started off with this really fast SpinEcho, it just wouldn't make any sense at all, and so that's why we went through the slower, easier to deal with ones. And so we'll start with 3D fast SpinEcho first. So one of the problems we said with collecting slices is that there's a limit on how thin you can go on the slices. So you can make an image that has a lot of pixels in the, looking down on the slice, but the slice is pretty thick. And it's nice to have pixels that are the same dimensions in all the axes, because otherwise you get a bias depending on what direction your slices have been recorded in. So the image will only be blurred in one axis, but it won't be blurry in the other axis. So it's kind of a little bit of a strange effect. That doesn't sort of normally happen out in the real world when you're looking or cutting into an object. So if you do a 3D version of a scan, it's much easier to get thinner slices, and we would put slices in quotes because you're actually not activating slices when you do a 3D scan. What you're doing is you're essentially stimulating the entire brain every single data point, and so you don't really have slices until you actually do the inverse Fourier transform, and then you end up with slices. So the scanner interface is a little bit inconsistent. It'll say how many slices do you want? It's not really slices. It's just how many data points in the KZ direction are you recording. That's actually what the slices parameter changes. So in general, it's going to be better than a 2D sequence because every single data point comes from the entire head, and so your signal to noise is going to be better because you're just recording a lot more data. And so what is our basic 3D fast spin echo sequence look like? So the sequence is quite simple. So basically we start off with a 90. And then we have the x, the y, the z gradient, the y gradient, the x gradient, and then what comes out. So here's the RF in. Here's the so-called slice select gradient, and here's the so-called phase encode gradient. Here's the readout. And here's the RF that signal is coming out. So So the first thing is we select a slab. So this is a slab select. We still don't want to activate the neck, and so we essentially do a very thick slice that's like the whole head, and then there's pretty much almost nothing to the sequence. So this is the slice select direction, or the partition direction as we call it, and then we do 180 here because it's a spin echo, and then we expect this amount of time afterwards we're going to get an echo. So down here we get our spin echo, and then over here there was an FID that we ignored, and since we're doing a slab select, we have to do that, little funky little ears. We have to pick out the slab for our 180 also. And that hopefully shouldn't make any signal because it's a 180. Then we have to go once to the left side of to the right side of K-space. Remember, like the very first time we have to go to the right side, but then since we're doing 180s that always stick us back on the left side, we only have to do that once. And usually what happens is we add a little extra on there, a little extra crusher, go a little bit past the right side of K-space. We got some extra, that's some extra, little extra. And then when the echo comes, we have to do the readout. And but before the echo comes, since it's a 3D sequence, we need to try all these different levels of the second phasing code direction and all these different levels of the first phasing code direction. So that means like for every one of these, we've got to do all of these. And so then we're ready to record some data, and usually what people do is they've got another little crusher on this guy. Oh, sorry, wrong thing. So let's put a little ear on this one. That's sort of, since we had a 180, it kind of fixes up this extra business here. And we go across and then put another little crusher like that. So that's our readout. And so then we record the data here. So here's, that's our data point for one line of K-space. And so this is, and then once we've done that, we're ready to repeat. And so how do we repeat? We wait, that amount of time again, do another 180. So we only do 190, and so then we do another 180, and then everything can repeat after that. But before we do that, 180, we've got to do our fixers. So we have to sort of like undo the phasing code that we did, and the partition direction phasing code, and we have to do the phasing code direction phasing code. And so these are, if we were going through in that direction, then on the way back we got to undo that. And so at this point we're finally ready to, so that's the unit, the repeating unit. So now we can just repeat this. So that's a 3D fast spin echo. So it's exactly the same as the non-3D fast spin echo, except we just have this extra phase encoding. And so this this guy, is called the partition direction, which is like the second phasing code. This is the first phasing code, which is, the partition is just the same thing as the first phasing code, except it's in a different direction, and this guy is the readout. Okay, so that's 3D fast spin echo, and it repeats, it repeats from here. So so here's the repeat. So the repeat is like this. So I just repeat this a bunch of times. So what's the problem with this? Well, one of the problems with spin echo in general is that you have a lot of 180-degree pulses. And so one of the problems with that is SAR, which is the specific absorption rate. And so how does this actually, what does this mean? This means like, how strongly are you microwaving the subject? And so the rules are, you can only raise the temperature of the subject by about 1 degree. So how does the scanner actually measure this? So the scanner, it actually directly measures how much RF has been absorbed. There's actually an antenna, another little detector inside there. And so what happens if you do an RF pulse, turn on the transmitter, that will generate some radio waves. They'll go into the head, and a certain percentage of them will be absorbed and will affect the spins and invert some of the spins. Like at the quantum mechanical level, it'll sort of make some that it'll flip some so that they're opposite orientation from the B0 field. And it will line up their phases. But all the RF power doesn't get absorbed because, you're not a very good antenna. You don't have a lot of metal in you, and like if you stick some metal in the microwave, more energy gets into it. So we're not a very good antenna. And so most of the RF is still sloshing around. And so RF are radio waves that propagate through, can propagate through a vacuum. And so what happens is you just actually measure how much RF was left after we ran the RF pulse. And so you can tell from that how much went into the body directly. And so you carefully measure that all the time to make sure that it doesn't get too high. And so what is the problem? Well, the problem is that this is sort of approximately proportional to, that's what we're saying there. So the RF is first proportional to the B0 squared, approximately. So that's one of the reasons, as you up the Tesla, you have more and more problems with B0. Now, why do people want to up the Tesla? Because you get more signal, because energy equals frequency, basically. So if you operate at a higher Tesla, you're operating at a higher frequency, you're operating at a higher energy, you get more signal. And so generally, that's why like a 3T scanner has a lot more signal than a 1.5T scanner. But there's problems because as you up the B0 field, for any given sequence, you're going to square the amount of RF that you're depositing into the patient. It's also dependent on the flip angle squared. So if you double your flip angle, that means 4 times the RF. And in practice, this is just an approximation, so it could be as much as 6 times the RF power for a 180 compared to a 90. So that's a big difference. And it's also dependent on what is the range of frequencies that you're using. So if you're using a hard pulse with a lot of different frequencies in it, that's going to also increase your RF power. So this is a problem, especially for a pulse sequence like this that's going to have like a zillion 180s, because remember how many lines of this we have to, this is just one line of data, might have 256 points, but we need to collect 10 million of these, 10 million data points. So we're going to need like 64,000 repeats of this. So 64,000 180s, that's a lot of 180s. And so there's a problem with this. And what is the problem? It's just not quite fast enough to get a whole volume of the brain, partly because of these RF limitations, because we can't go as fast as we could just in terms of the total amount of time, because then we would heat up the person too much. So, so not only does the scanner, I'll just go back to sort of the safety measures, not only does the scanner measure how much RF got absorbed, so it can tell how much it heated you, but it also has a model of how long it takes the heating to go away. And so for something like the brain's a particularly safe thing to scan because it's got a huge blood supply, because like 10 or 20% of your whole metabolism is just supporting the brain. And so if you heat up the brain a little bit, no problem, like the blood's going in and out, and so it'll completely, it's like your finger, like you have a good blood supply in your finger, and so if you heat up your finger, it will quickly get back to normal temperature because there's blood going through it. There's other things that are not so good, like the cornea is an example. The circulation in the cornea is much more slight than the circulation going through the brain. And so basically you make a model of how the body heats up and what part of the body you're actually scanning, and then you have a model of how long it takes that heat to be dissipated. And so that's actually also built into the scanner. So it's measuring the total amount of RF deposited, and it's also making a model of how long it takes that heat to go away. Depends on body weight. So, if you're bigger, you'll absorb more RF, but you've got more stuff to actually sort of get rid of the heat. And so all those things are carefully monitored and make sure that you don't actually heat up. And so it's pretty much a hard limit. You can't go over that limit. And so what did people do? Well, you can imagine sort of a whole sort of spectrum of different ways of doing it. So we could do slices, or we could do 3D whole brain. So here's our whole brain. We could either do 2D slices, but there's stuff in between, and the stuff in between are, why not just divide the brain up into 2 chunks and do 3D up here, and then 3D part B down here. So you could just do 3D across the entire brain, but the problem is we're not quite fast enough. It's not really fast SpinEcho. And so what you could do is, let's just record this slab and do that slab in 3D, and then do this slab in 3D. And so you can do that. It's kind of like, so this is like, slabs, like, multiple 3D slabs. So there's no slices within each one. Each one is just a 3D volume that you're doing a 3D Fourier transform on. But this way, if you do it this way, you can record some of the data in this one when this one is recovering and you're not heating up this one. And so that's another way to fix it. But the problem is, the boundary is kind of a mess. And so you can record a little extra and then overlap them and throw away some of these. And so this sequence was around for quite a while. In the 90s already, we had this sequence. I used it once on a preserved dolphin brain. If you go to the MRI center, you can see a reconstruction of the dolphin cortex using a sequence like this. But it never got really popular. In the it's just kind of for clinical use, because it's always a little fiddly. You got these 2 slabs. there's boundaries between the slabs, a lot of some artifacts. So that's 3D fast spin echo. So it's faster than 2D fast spin echo, but it's not quite fast enough. So any questions about sort of 3D fast spin echo as I erase it? So same as, 2D, except you just have like another set of gradients in the slice, like in the slice direction. Okay, so about maybe 10 years ago, somebody just figured out how to do really fast spin echo. So that's what we want to just go over. And as I mentioned before, like the regular spin echo is straightforward. You do a 90, 180, you record some data. That's all sort of straightforward. And then fast spin echo is kind of a little bit funky because you record, do a 90 and then a whole echo train. And you have to sort of like fiddle around with the phases, fiddle around with the gradients to make sure that you undo all the things you were doing during the echo train. But the problem that really fast spin echo, solved was the 180s. And so the problem with the 180s is there's just too much power in the 180s. And that is one of the things that stops you. The other thing that stops you is if you're doing an RF pulse, so like here's a little sync RF pulse like that. If we just sort of strip down what happens in the sequence, you do it like an RF pulse, and then we turn on the gradient and do some recording, and then when we're done, we immediately turn on another RF pulse like that. And so the problem is, it's hard. And how fast is this going? This is going pretty fast already for 3D fast spin echo. So this time might be, say, like 8.5 milliseconds. So think of how fast that is. That means more than 100 times a second you're doing this. But part of the problem is that it takes a while to play out that pulse, and it's hard to sort of like get much. If you could do it faster, then you could collect more data. But there's several things stopping you. One is this pulse is kind of long, and then the second thing is if you scrunched it even more in order to collect more data, you're going to end up with there's the length of the pulse, but then you're going to end up with too much RF deposited, because if each one of these are 180, you'll get too many 180s together. So what's the problem? I mean, what's the solution to it? So the solution to it was, well, why don't we just not use 180? But it turns out, if you don't use 180, then what's going to happen? You're going to get stimulated echoes. But it turns out that's a feature, not a bug. So I'm going to put 4 different ways of fiddling with the flip angle and how much signal you get out, to sort of like just go over how they develop the sequence. And if you want to read about this, there's a reading in the paper by Mugler. You can actually look at what I'm going to go over here. So if we start off, so let's start off. We'll make 8 of these guys. So what I'm plotting here is time versus flip angle. So we're leading up to the final answer, which is down here. So in each case, this is milliseconds here. So time's going that way. And then on the other axis is the flip angle. So this is degrees. Degrees flip. Milliseconds. So the first thing that we do is what happens if we just do 180s. And what the graph is plotting, so there's so we got two axes, so milliseconds and degrees of flip angle. And then what I'm plotting on this side is the echo amplitude. Echo amp. So what is the actual strength of the echo? Also over time. So it's all over time. So what is the first starting point, which would be like the 3D fast spin echo? Just do 180s. And then also, what is the axis here? So we're going up to a really long time, 800 milliseconds. So 0 to 800. So that's really, now how on earth could you get up to 800? Because we know that like T2 is about, say, 50 milliseconds, something like that. So like after 50 milliseconds, most of the signal has gone away. So how could you do anything at 800? That's where the stimulated echoes come in. So it's not really fast spin echo. It's like really fast spin echo plus stimulated echo. So our first thing is, let's just plot what happens when we just do 180s. So the 180s for, over 800 milliseconds. And so, what happens to your signal? Well, your signal, dies off pretty quickly like that. So that's so this is, the signal, this column, and then this guy is the flip angle series. So if we just do 180, I forgot to put the 180 here. Okay, now all the graphs are labeled. There's very little signal to deal with sort of later on. So what we could do instead is, why don't we just do, say 60. So now what's going to happen, we're going to get some stimulated echoes, because whenever you do 3 RF pulses that are not 90 and 180, you're going to start to get these stimulated echoes where you flip some of the magnetization that's in the transverse plane, where it decays into the longitudinal axis, and then it's kind of saved there. And then when you do another echo, it pops it back out of the longitudinal axis, and then it starts rephasing it to give you the echo. And that case is called a stimulated echo, where you've saved it temporarily, where it doesn't decay very much in the longitudinal axis. And so what will that do to the signal? So if I plot the original, here's the original one on all of these like that. It falls off a little quicker than that, but I'll just leave it like that. So what does it look like now? So if you just do a 60, you get something, because of the stimulated echoes, is a little better. It's a little better, not that much better. partly because it's a little better, even though it's only 60. So that's kind of a good thing. We beat what we had before, doing all these 180s, only doing a 60. And so then they said, well, let's, what if you do something like this, like, start off high and go down to a 60. Then you'll get rid of that little blip at the beginning, and you'll get something that sort of goes like this, but it still doesn't go out too far. And so what do they actually do in really fast SpinEcho? Just a complicated, optimized weirdness, like start up at about like 120 and then go way down to like 30, and then come up like this, and then at the end do a funky little thing like that. Okay, so if you do that, what you get is something that starts a little lower than you would have gotten with fast SpinEcho, but it comes across like that. And at this point right here, it's about 10 times the signal. So it's like a huge win. So you basically would have gone down to virtually nothing, but at 800 milliseconds, that's a full second later, you've actually got a decent signal to work with. And that's the thing that really, and then on top of that, you're really cutting down your high energy deposition, except at the very end there. So this sequence was, surprisingly, it was originally developed for imaging the abdomen. I don't know why, they just didn't suggest using it in the brain. And so what happened, the Human Connectome project was a big scanning project to do a bunch of standardized data that multiple different research groups could work with. And so they sort of looked at this and they said, wow, you use it in the brain. But amazingly, like if you went to the Siemens scanner, it was under the abdomen, under the abdomen. So you got to look around, like you don't just concentrate on the brain, like look around all the other protocols. And so how does this work? So now that we've got a signal that will last a long time, we can do endless echo trains. So we can do 150 echoes, 270 echoes, huge numbers of echoes. And so now it'll give us enough thing to do really fast SpinEcho. So what does the pulse sequence look like? So it's sort of deceptively simple, so it's not much to it. So 2, 3 signal. Okay, so we start off with just 190. So there's a single 90 at the beginning, and then we're going to make 200 echoes out of it. And so one of the problems that I mentioned before is that if we use a pulse that's like a sync pulse, it takes a while to play it out, and then you're just kind of wasting time. So we'll still do a slab select for the first 90, but then after that, just do a hard pulse. And so what is a hard pulse? You can do that very quickly. That's just like turn the transmitter on and it just goes ding. It just like wiggles a bunch of times and you just turn it off. And what does that do? That sort of, if you do this on the transmitter, you Fourier transform that into what that means in frequency, and it means like a sync, but it's a really wide sync, and so it's effectively just stimulating the entire. So this is a hard pulse. That's really quick. And don't bother turning on any slice select gradient, because that would just slow you down. So you've flipped a set of spins, but now once you've flipped those set of spins, just stimulate everything. And then what do we do for? Oh, there we are. So what do we do for that? Then we just so here's the your hard pulse. And so as soon as the hard pulse ends, immediately start doing our phase encoding. So here's our phase encoding in the partition direction, and then do our phase encoding in the phase encode direction, and then do a slightly little ear sort of readout business like that. And then we've got just a single one that occurs once only with a little bit of extra on it here. So this is once only. So this is RF in the Z, Y, X, RF out. Okay, and then as soon as we finish this, we immediately fix up what we did in the phase encode, because we got to use, we have to patch up our echoes because we need to reuse them. And so if we were, say, going in this direction, then on the way back we go in the opposite direction. And so now we're ready to go again. And so so now we just do another RF pulse. Now the amplitude of those pulses are changing because you're doing this to them. So sometimes they're so these are variable flip, because we're doing this strange thing to them. But now they managed to jam everything down to, so now we're repeating. So here's the repeat. So they managed to jam everything down to 3.9 milliseconds. So that is really short. So that's so that means you can do about like 250 of these. And so when you hear this sequence, you just hear like, and that's like 250 data point recordings coming out, because it's going so fast. So here's where you're recording. Now it starts to get a little more complicated, because at this point we would expect to get, so at this point right here we have the initial FID, which we ignore, and then at this point we get an echo, and that guy's a spin echo. But now what happens for the third one, we're going to get, so after the third one, so you'll get another spin echo over here. But after the third one, right here, because the second one saved some transverse magnetization in the longitudinal plane, when we do the third one, it will uncover that transverse magnetization, uncover that longitudinal back into the transverse plane, but sort of flip it and cause this rephasing to occur. So basically this guy will be a stimulated echo, plus a spin echo plus a stimulated echo. And that's good, because if we actually look at the equation for the stimulated echo, it has a term in it. So it has a term in it that looks like, so this guy, includes a term that is, minus tau 2, that's the time between the second and the third pulse, divided by T1. And T1 is long compared to T2. So that means it doesn't decay very much. And so, because of that, that's actually what's explaining this part here, why the signal So this is STE amplitude equation includes. It includes that, and so that's a good thing. So that means that it doesn't decay very fast. So that's why we can end up with an echo after 800 milliseconds. So you can see it's but it's a very simple sort of simple looking pulse sequence. I'll just draw one more repeat in here. So the gradients are hammering back and forth, and the flip angles are not too big. We're not heating up the subject too much. So we're going at least twice as fast as we were before, but it still wasn't quite fast enough. So, and this, onward, to 200 echoes from 190 degree. Okay, still wasn't quite fast enough. And so what's the final insult on how to actually really speed it up? And so how do you really speed it up? Well, you sort of leave out some of the data. And so what does that look like? So we'll draw two different pictures of how they're sort of leaving out some of the data. And so what I'm drawing here are the 3D K-spaces. So, and I'm going to draw it for a more proton density weighted one and a T2 weighted one. So the top one will be the T2 weighted one. So this is our three-dimensional K-space that we're collecting. And so what are the axes? So this direction is the readout. So that's so this guy is, partition, and phase. And this guy is the readout. So that direction is the readout. So that's the KX direction. And then the other directions are the KY direction and the KZ. So what controls? So the Z and the Y gradient, all these phasing code thingies, are what decide where you are in this plane. And then for each point in that plane, you do a readout. So that's the same down here. So what's the first way to save points? Basically, just record a lot of data in the center of K-space, and then when you get out to the outside of K-space, record less data, because we know that the center of K-space is particularly important for controlling the contrast. So just start leaving out some data points. Don't bother recording all the way out to the edge like that. So just record like a cylinder of data. So throw this away. That's kind of extra high frequency. Don't mess with that. So throw all that away. That saves a little time. And then do like a tricky method. So like the way I've drawn it here, it's like for each setting of, like for this setting of the Z gradient, do all of these ones of the Y gradient, but that takes a little more time. So let's do it in a trickier way. And so if we look at each of the echoes, so these are sort of the echo number here. Echo number. So where are the different echo numbers happening? So they're happening they're happening as you go across ky. So here's the echo numbers. So these are what echo do we have? Like, so here's like, echo, 5, echo, echo 15, what is it, echo 45, etc. So that's the echo number. But what are the actual, but we got this complicated mess here because we're denser in the middle. So what is the, what are the actual sort of individual echo trains, like 1 time through for 190 look like? So here's that, they're denser in the middle, so we've got to somehow sort of accommodate that. And so what happens is we have, so like here's the, and we're throwing away the, don't forget to throw away the edges, don't bother with that. So here's our first echo train goes like this. And so why do we do that? Because we don't want to record the center of k-space right at the beginning because we want something that's T2 weighted. But then, because we're sort of more denser, we've got to go through a little bit, a little bit differently, depending on, where we were. So this is like, echo train, this is, train 1, and then that one up there is like, trains 6. This one is going through the middle, train 16, etc. And what does this mean here? This means like, how do you get to a particular point here? It's some combination of these two guys, the z and the y gradient, and then you record, you record a data, you do a readout at that point, and then you set them. Well, you undo whatever you did, and then set them to another thing. So you can see you're not going through in sort of like the straightforward way here, because you're sort of like making the ky go up and then making it go down, complicated mess. But the end result is that you record the center of k-space a little bit late so that you can get a T2 weighted scan. So this would be, so this guy would be a long TE effective. And this is kind of like a doubly effective, for T2 weighted. And this is sort of like doubly TE effective. So we have, we started off with, TE. So what is TE? TE was we record the signal at some point right here, and we hopefully get, a contrast difference between the two. But then we said, well, when we have fast spin echo, what we do is we have TE effective. And what is TE effective? TE effective is whatever the time that you recorded the center of k-space. And so in TE effective, what happens is here's the thing falling off, and you're recording all the hell all over the place like that. But you record the center of k-space. The center, equals what you call TE effective. But now we have TE effective. And so what is that? So now, because we've done all these stimulated echoes, the echo train lasts 10 times as long. And so by the time we actually get to the center of k-space, it might be like 300 milliseconds or 400 milliseconds. And so that's supposedly the TE effective, but it's not really. It looks like a TE of like 50. And so what they do is they put a number, a much smaller number. So like, essentially compensate for for the stimulated echo, or STE. So not only is it the time that how long did you go through the center of K-space, but that number is going to be like 300 milliseconds. That doesn't compute. Doesn't seem like any reasonable echo time. It's way too long. And so then they modify it again. And so then you look on the interface to sort of set a number that is sort of similar to what you would do if you were doing a fast spin echo sequence, but in reality, it's 10 times as long. Yeah, so you can begin to see like what the problem is after you really start optimizing these things. And we've got a similar, so this one was, that was a long, so this is a short TE effective, for proton density weighted. And in this case, we have to, we're just recording more in the center of K-space like we were before. But in this case, we've got so much signal that we can just chop off part of K-space. So just don't bother recording this. And how could we do that? Remember, that was because of the funny symmetry of K-space. We can reconstruct, we can reconstruct what this data should have been from other parts of K-space because of the Hermitian symmetry. And then the way you're doing the echoes here are you start in the middle and then you go circularly through K-space because we want sort of a short effective TE. And then the way the actual sort of echo trains look, they come out in a strange way like this. And they come up like that after chopping off some of the K-space. So that's, KY. So this means like instead of doing just that simple for each GZ do all the GYs, instead you're doing some weird combination of GZ and GY to go to a particular place in K-space, and then once you get there, of course, at each one of these points, we then record our train of echoes. So these are the different train of echoes. So I think this is the first one. This is the 15th train and the 30th train. So you can see it's. I didn't title this one. This was echo train number. So there's one of these for each 90 echo train number. It's sort of like the partition direction, but it's not because it's a combination of a particular combination of GZ and GY that's not just going through in a simple loop fashion. So why did I go through all this? This is a scan that you just routinely use. You can get a T2 weighted scan. So like T2 weighted scan, in like 3 minutes with 0.9 millimeter cubed voxel, and so that is so much faster. It's like 10 times faster than regular fast spin echo, or 20 times faster. And so you just use it. But to understand how it works, you can see, wow, it's quite we've created quite a monster here that's really pretty hard to understand how it works because it's so optimized. And like I said, that's just because I'm older and we got to do all the easy stuff, and now everything's really hard. It's unfortunately just the way it works, and it's gotten sort of more and more twisted and optimized. Sort of getting more biological. That's the way biology is. Biology is like ultra super optimized. That's why it's so hard to understand, because there's so many little tricks and interactions, and this is like that, starting to get like that. There's all these different little tricks and interactions. But the bottom line is it goes really fast. And so so this is, you know, used more and more these days. Okay, so sorry I didn't leave any port in the diagram here for my face. So any questions about really fast SpinEcho? Sort of clear. You can sort of see, like, you know, approximately how these optimizations are happening. It's kind of, I think you could probably go even faster than this if you do, you know, some of those things that I was talking about in the 8 a.m. lecture, where you did some kind of compressed sense, where you know, instead of just leaving out the corners of K-space, you left out some data, you know, inside of K-space, and then you could probably end up getting an image like this in 1 or 2 minutes, and so that's definitely good, because you could do all different kinds of image, or you could just do a higher resolution image. Okay, so space scan. So started off with sort of SpinEcho. That's just a 90 and a 180, and then fast SpinEcho 2D. That was 90, 180, 180, 180, and then 3D fast SpinEcho. We just added some more gradients in the on the z-axis, and then like really fast SpinEcho. It's not even really SpinEcho. It's really fast SpinEcho plus stimulated echo. And instead of like viewing the stimulated echo as a bad thing, it's actually a good thing, because it gives you this, it allows your signal to continue for much longer. But the contrast is not going to be the standard SpinEcho contrast. It'll be a little bit different because of all the stimulated echoes. The equation is more complicated, and it's got this, you know, T1 factor in it. So, but we're going so fast, we can wait quite a long time. So we can still wait, like, you know, 4 seconds or something like that until we do another 90. So, you know, eventually we do another 90, but we can still have, you know, a TR of like 4 seconds, because we're collecting the data. We're using up so much extra time to collect the data in between that we can afford to have a long recovery time, so we don't get any T1 waiting. Okay, so yeah, if you want to see it, you can read the Mugler paper and just sort of see all these optimizations. The basic concept's pretty much the same, except that you suddenly said, oh, instead of trying to get rid of stimulated echoes, let's use them. Because a lot of times stimulated echoes are quite big, and they cause image artifacts if you're not expecting them. And so a lot of times people just try to eliminate them instead of just trying to take advantage of them. Okay, any questions? Stunned silence. What? Sort of makes sense. A little bit, yeah. So, you know, when we're thinking of these pictures this way, you know, each one of these particular locations in here is some sort of physical stripes, you know, going across the brain in some direction. But this is like a shorthand for just thinking about it in terms of where you are in spatial frequency space. And, you know, basically where you are just depends on, you know, what you set the gradients to. That just moves you to a particular location in there. So, you know, each of these little fixtures, what they're doing is they're essentially sort of undoing whatever you did to get to this point in K-space. So just undo whatever you did and go back to the right edge. Okay, any final questions? Homework going okay? Messing with the homework? There's a lot of problems on there. Don't worry about the last one. The last one is you don't have to do the last one if you don't want. It's if you want to bang your head against the wall, try the last one. Okay, any questions? All good? I don't believe it's good. You can sort of see the flow of things. It's not completely out of control. It's just like, a lot of details. But it relates to the stuff we talked about before, like spin echo and stimulated echo. Okay, I think we'll finish it up there.